Welcome back. So far we have seen how to derive the equations for oblique shock waves, and which we have derived using the normal shock relations by noting that the m1 mn1, that is we call the normal component of the Mach number, upstream Mach number mn1, and we have written this as m1 sine of beta, where beta is the wave angle, and subsequently we have used the relationship between m1 and m2 for a normal shock, and we replaced m1 with m1 sine beta, and we have obtained mn2, again using the triangle, velocity triangles, which we have shown in our earlier discussion, and we have brought out the relationship m2 is equal to mn2, which is again the normal component of the Mach number upon sine beta minus theta, where theta we have said this is deflection angle or wave angle. And now we will moving to our further discussion that since we have used the normal component of the Mach number, upstream Mach number, which is indeed perpendicular to the shock waves, and hence this normal component also must be supersonic, so that it can cross the, or it can generate a oblique shock into a normal shock for this component, which is I am writing here mn1, and hence just we can ensure that m1 sine beta, that is inherently mn1 normal component, must be greater than or equal to 1, and hence this gives a very important and useful information, because if you write this sine of beta, this gives, I can rewrite as 1 upon m1, and hence beta can be written as greater than or equal to sine inverse 1 by m1. That means when inequality becomes equal, then I can replace this m1 sine beta as mu, which is n equal to 1, as I have shown over here, and hence this mu again an angle which we call Mach angle. That means this is the case, that is when the normal component of the Mach number is just equal to 1, then an oblique shock degenerates into a wave called Mach wave. That means the minimum angle which is possible for a compressible flow of a wave is nothing but sine inverse 1 upon m1. Another case, that the limiting case on oblique shock, we can rightly see here that beta maximum is pi by 2, which is the case of a normal shock wave, because this wave normal shock is perpendicular to the upstream flow direction. Therefore, the range of beta, which that is beta lies between the range sine inverse 1 by m1 is less than or equal to pi by 2. This is the normal shock case, and this is the case when the oblique shock degenerates into the Mach wave, which has the property that changes in the property across the Mach wave are negligibly small, and you can neglect that. Now in this case, now we can see that in a compressible flow regime, the Mach wave, compression fronts, expansion wave, all are present. We have stated couple of times that in any supersonic flow the shock may or may not occur, but Mach waves are always present inside a flow situation. Now the question arises, why these Mach waves are present? What is the root cause of having these Mach waves? That is, we should understand that if, let us say, for example, in a wind tunnel test section, something like this, where you have mounted your model assuming completely isentropic flows, but you have mounted the model for your measurement. But we should see here that the test section wall are not smooth. Even you try your level best, a perfect smoothness of the surface is a theoretical assumption. And since the roughness is always present on the wall of this test section, the Mach wave will always be present. Now, about the Mach wave, we should also understand that the Mach wave, a set of Mach wave in a two-dimensional image or representation, these Mach waves, they go and intersect other set of Mach waves. These Mach waves are categorized as left running and right running. Assuming that if we are moving along the flow direction, then the left running Mach waves are these, whereas the right running Mach waves which are coming right here are these, and these Mach waves intersect each other, and these are linear waves, and it is assumed that these Mach waves which are intersecting each other, before the intersection and after the intersection, these Mach waves will remain linear, and that is why they are called simple waves, and the reason they traverse these simple waves are called simple regions. Now, a very important relationship about oblique shock wave is termed as theta beta m relationship, that is the deflection angle, the shock angle, and the Mach number relationship. Again, I am redrawing here the oblique shock and resolving the velocity components as shown in this figure. The V1 is the upstream velocity, and Vy1 I am drawing parallel to the shock wave, and Vx1 is our normal component of velocity upstream. Similarly, in the downstream side, the V2 is the velocity which is coming from the wave when the flow is coming from the wave, and resolving this into the normal component and the tangential component. Make sure that again, since there is no flow parallel to the shock wave, and hence the velocity component Vy1 and Vy2, they are indeed equal, and hence the only change which is occurring in the normal component of the velocity Vx1 and Vx2, and by this diagram itself we can note it that Vx1 is reduces to Vx2, that is Vx1 component of the velocity is greater than Vx2. Now, from this schematic diagram, using the trigonometry, we can write down that if the shock is present or is making an angle beta here, then resolving this and the flow deflection, that is the flow coming out of this shock wave, is making an angle theta, which is nothing but wedge angle or deflection angle. Wedge angle means if the surface is something like this and turning into itself, and hence since the flow has to be parallel to the surface and that inclination of the surface is theta, and hence I am representing here the deflection angle as theta. Now, using the trigonometry, I can write down tan beta is equal to the perpendicular upon the base, that is the Vx1 divided by Vy. Rather than using the 1 and 2, since they are equal, I am just writing them as Vy. Similarly, on the right hand side, I can use this triangle, I can take this triangle and I can write down that is tan beta minus theta is equal to the normal component of the velocity which is coming out of the shock Vx2 upon Vy1. Using these two relationships, that is dividing secant by 1 and using subsequently the continuity equation I can write down further as tan beta minus theta upon tan beta is nothing but small v x2 upon v x1. And using the continuity equation I can directly write down this is the inverse rho 1 upon rho 2. Now this rho 1 by rho 2 is the static density ratio which we have already derived for the normal shock as well as oblique shock wave. Writing this rho 1 by rho 2 on the right hand side, I can write down the full equation as tan beta minus theta upon tan beta is equal to gamma minus 1 m1 square sin square beta plus 2 upon gamma plus 1 m1 square sin square beta. Now using again the trigonometry relationship for tan beta minus theta, I can open this fellow as tan beta minus tan theta divided by 1 plus tan beta into tan theta. Now using this relationship on this side I can reduce on solving, I can get this form tan theta is equal to 2 cot beta m1 square sin square beta minus 1 upon m1 square gamma plus cos 2 beta plus 2. Now what we can see here, if we put beta for a normal shock case beta pi by 2, I can readily see it that this fellow that is the right hand side, the whole expression becomes 0, and hence when the tan theta is equal to 0, what we obtained here that this tan theta will be 0 when beta is equal to for one case pi by 2. Secondly, if I put that is the whole m1 sin square beta again is equal to 1, that means I am trying to put the beta as sin inverse 1 by m1, then again what I find the right hand side becomes 0. That means the tan theta in the range which we have already said that beta is varying between pi by 2 to sin inverse 1 by m1. This in this range of wave shock angle which oblique shock can make with respect to the flow direction, incoming flow direction, what I find that theta is positive. Hence we know from our mathematics background that since at two different values a function is showing positive means it must have a maximum, and that maximum is now our main idea. And since in between these shock values, this of shock wave angle between pi by 2 and sin inverse 1 by m1, that is a Mach wave and a normal shock wave at two extremum, I am having theta positive. This relationship what we obtained here about tan theta and beta, this is called an m1, this is called a famous theta beta m relationship. If we plot this, we will get couple of very useful information. Once you plot this thing, this plot comes something like this: the deflection angle at the along the y axis and the wave angle along the x axis. The graphs looks like something like this. At various incoming Mach number, which I have shown here 1.2, 1.4, 1.6, 2, 3 and up to theoretical infinity. What we find that once we increase the Mach number, the graph shifts rightward, and what other things we can see here that these are the zones, that these are the points where the theta becomes maximum, because for any wave angle, variation in the wave angle, the spread of any particular curve is something like this, and then you can find that there is a maximum, and when we join these maximum for this various incoming Mach number m1 upstream Mach number, then this is joined by this dotted line. This dotted line represents the theta when theta is maximum, and the downstream solution, that is the Mach number, is represented as m2. You can see here that all these theta equal to theta maximum curve, the left hand side is denoted as Mach number less than greater than 1, whereas right hand side is shown as m2 less than 1, that is subsonic solution, and the left hand side is supersonic solution downstream. Now another useful information what we can see for a given deflection angle, which is generally mentioned in the problem, is that for a given deflection angle and for a given upstream Mach number, when the values deflection is for a particular Mach number, we can obtain directly by seeing this graph what is my theta maximum, and when theta is less than theta maximum, that is the maximum possible deflection angle for a given upstream Mach number. If we see this, that when the given deflection angle is less than theta maximum, what we can see that for any deflection angle, if you draw a line on that particular Mach number, let us say for here, what we can see, this line intersect at two different points on this graph. That means for a given theta and for a given m1, two wave angle we can obtain, that is two beta values we obtain. One beta values is lying in the zone which is telling me that m2 is greater than 1, that is the solution obtained downstream is supersonic, whereas the flow obtained for another beta which is higher than the first beta, if I say this is the beta 1 and this is beta 2. So for a given theta, when it is less than theta maximum, and for a given m1, I am obtaining two solutions, beta 1 and beta 2. For a beta 1, I am getting the downstream Mach number greater than 1, whereas for a downstream Mach number for beta 2 which is higher than beta 1, I am getting m2 is less than 1. This solution for which the beta 1, for which the downstream Mach number is still supersonic, we call weak solution. That means the oblique shock generated here is weak in nature, whereas when the downstream Mach number is subsonic for that given beta which is higher than the first beta at higher wave angle, this solution is called strong, and in turn we can say the oblique shock generated there is a strong oblique shock. Now the another case which we can take up, that what happens when theta is more than theta maximum. Then what we can essentially see here, that when the given deflection angle is greater than theta maximum, then what we can find for a given deflection angle which is more than the theta maximum, however the Mach number, let us say Mach 2, at Mach 2 if my deflection angle is more than this, then this drawing a line parallel to this will not intersect anywhere on this curve. That means in these circumstances no solution is possible. It signifies that in this case, for a given deflection angle which is more than theta maximum, the shock cannot remain attached to the surface, and this is the case of a detached shock waves which we generally encountered in case of a blunt body, where the given blunt body or blunt nose body, the theta, the deflection angle is more than theta maximum. However, this can also occur on a conical body, something like this, which is shown as 2D wedge. If theta is more than theta maximum, the oblique shock which used to remain at the vertex here cannot remain attached, and it moves slightly away from the and stands in this kind of zone. And this kind of shock, which is a detached shock, is also known as bow shock. Which is the case when a given deflection angle is more than theta maximum, that is the maximum deflection angle possible for a given m1, that is upstream Mach number. Now, an important point we can mention here that for all the naturally oblique shocks are weak in nature. That means wherever an oblique shock generated on its own without any special arrangement, those oblique shocks are weak in nature. However, to generate a strong oblique shock, you require a special arrangement. One such case is the intakes, which we will take up a short while from now. Now, we should understand and we should recap that what we have studied so far. We have seen that if the surface is something like this, that is, which is forcing the flow turning into itself, we found that this surface at the point where the surface gradient or slope is changing, here surface slope is changing, we are having a attached oblique shock like something like this, which has the property that in the limiting case, this can degenerate into Mach wave, a wave across which flow properties are very small and can be neglected, and hence whatever the incoming Mach number m1 will remain downstream also Mach number 1. These waves are called Mach waves. In the limiting case of beta, when it becomes pi by 2, we will get a normal shock wave. Now, moreover to this, there is also a waves called Mach line. The difference between this Mach wave and Mach line is that Mach waves are those isentropic waves across which the flow properties can be neglected, change in flow properties can be neglected. However, Mach lines are also real in nature, likewise Mach waves. Those are the lines which are always present, but across which the flow property is finite and you cannot neglect that, you must account it. In compressible flow regime, these Mach lines are replaced with imaginary lines called characteristic waves, and these characteristic waves are the backbone of method of characteristics by which the various geometries such as nozzles are generated in compressible flow regime. And these Mach lines, which are replaced with imaginary characteristic waves, are defined as left running characteristic wave and right running characteristic wave, as if you as the observer moving along the incoming flow direction, which I am showing here, that let us say if I am traveling along with this line, then my left running line denoted by negative sign here are left running characteristics, which are actually the Mach line, but I have replaced with the imaginary characteristics, whereas the right hand side is the right running characteristics waves. The Mach waves, must remember here, is that the Mach waves and Mach lines are real, but these Mach lines are replaced with imaginary characteristics waves, which are responsible for any isentropic change like accelerating or decelerating a supersonic flow. This is, as I said, this is the base for the method of characteristics, which is a very important tool in generating surfaces in compressible flow regime such as nozzles. Now, as I mentioned here, that all the naturally occurring shocks are oblique in nature and they are essentially weak in nature, and you require the special arrangement to generate stronger oblique shock. Please note down that if there is a very important application of stronger oblique shock. We know that ramjet and scramjet engines do not have any turbo machinery involved, and it has a very simple geometry. That means a ramjet engine which has a intake and after that it has a combustion chamber, and further it has the nozzle to exhaust the gases so that it can gain the thrust. A ramjet, we know that it cannot fly on its own, and you require the supporting mechanism to achieve a particular Mach number, after that the ramjet can fly on its own. How it is possible? This is possible because of intake or inlets present at the entry point of the ramjets. What happens there when the Mach number, let us say Mach at the incoming Mach number of Mach number 4 for example, then this flow which is entering air, which is entering inside the inlet, requires a proper compression, that the air must be compressed on its own first, so that it can enter into the combustion chamber for a stable combustion. The ramjet requires the proper combination of shock waves which are oblique and a terminating normal shock, which can reduce at the same time the flow speed from supersonic to low subsonic, as well as it also compresses the flow from a high static ambient pressure to a higher pressure, such that as soon as it mixed with fuel in the combustion chamber, it can sustain or it can lead to a stable combustion for flying. This is done by inlets or intakes in the ramjets. One such application I can show it here, that there is a contraction ratio, two contraction ratio images I have shown. The contraction ratio of an intake is defined as the flow capture area to the inlet area, and likewise I have shown here 1.19 if one particular case, and another is higher contraction ratio of 1.32. You can see here for a intake with 1.19 CR, that is contraction ratio, at Mach 2 you can see here the shock waves which are very weak in presenting here. However, as soon as you start the flow at higher contraction ratio, what you will find that these are the shock waves which are generated, and moreover at the cowl generated these shock waves, you can see the stronger waves here shown by the black color lines here, and then these shock waves, when they come and hit the bottom surface and then get light reflection because of real body present here, these kind of wave structures are present in this region of the intake. The video here, we can see here that when you start the intake, then when the flow was not present, no shock was formed. However, once we start the intake, then these many shocks are present here because of the surface geometry changes. Now in this particular case, I have used two ramps of, that is one from here and another from here, that is a double ramp, and once you start a supersonic flow at Mach 2 in this case, then we can find from all the corners many waves are generated, and these waves are generated and they are coalescing into each other, and then they becomes very strong in this case. Since these are and at this point also, when the flow which is entering here fully, then these at this tip also a attached oblique shock, because a conical tip, a sharp nose here it is finding, and hence it is in this case theta is less than theta maximum, and hence an oblique shock of something like this is obtained. And likewise the shock cell structure, the shock structure we are finding inside the region of the intake as well. These shocks are since generated using this special mechanism of intake, and hence all these oblique shocks are stronger waves, and which delivers a incoming Mach 2 air with higher pressure. And also you can note it down that there is a terminating normal shock as well, which is required, generated by this mechanism, so that if all these oblique shocks after which the solutions are still supersonic, then it will again further reduces to subsonic speed before entering into the combustion chamber. Now, moving to a very useful form of this theta beta m relationship we can deduce from here. We can note that for a small theta we can use the trigonometry, that is sin theta will be almost equal to the theta. Hence, the theta beta m relationship originally found, we can write down that m1 sin square beta, m1 square sin square beta minus 1 can be written as approximately gamma plus 1 by 2 m1 square tan beta into theta. For a given small deflection angle, the wave angle, the beta is also small, and hence even though the sin beta can also be written as beta, though it is very small, but once it is having a product at m1 which is very large, then m1 and beta product cannot be neglected, because m1 beta product is also very larger than 1. In this case, this relationship which is obtained from theta beta and m can be reduced as beta is equal to gamma plus 1 by 2 into theta. This is actually a case of hypersonic flow, where at high Mach numbers the shock angle is gamma plus 1 by 2 into theta. Note down here that when the upstream Mach number is high, if gamma I am considering about an air, we can readily see here that beta is approximately 1.2 times of theta, that is for a given deflection angle the shock angle is 1.2 times larger than the given angle, and this eventually will see the case in the hypersonic flow once we will take up that. Now, since the shock can be approximated, that means a oblique shock can be degenerated into a Mach wave or Mach line. As I said, if it is degenerated into Mach wave, then beta will be approximately equal to mu. Considering this particular case, when oblique shock is degenerated in the form of Mach wave, then I can write down sin beta approximately equal to sin mu, which can be written as 1 by m. Now, using this again the trigonometry, we know that sin square beta plus cos square beta is equal to 1. That relationship if I am using, then I can get cos beta as 1 by m square root of m square minus 1, and divide for the tan beta which is equal to sin beta upon cos of beta. I can write down tan beta is equal to 1 upon square root of m square minus 1. Now, this relationship, if I will insert it back to the original equation which is 1 here, I can write down as m1 square sin square beta minus 1 is equal to approximately equal to gamma plus 1 by 2 m1 square upon square root of m1 square minus 1 into theta. Now, we know from our static pressure ratio of an oblique shock wave relationship which is written over here. Since m1 square sin square beta is deduced like this, if I insert the whole upper bracket in the numerator here with this, replacing this, I can obtain P2 by P1 is equal to 1 plus gamma m1 square upon m1 square minus 1 into theta. But note it down, the strength of the wave, we have already written that P2 minus P1 upon P1 is we call the strength of the wave, which we have earlier denoted with capital P. Using this relationship, if I will move this fellow as on the left hand side, I can write down the strength of the wave is nothing but gamma m1 square upon square root of m1 square minus 1 into theta, which I have written it for you here. Now what we eventually see it here, for a finite pressure change, that is the finite strength of the shock wave, I will see here that the strength of the shock is directly proportional to theta for a given upstream Mach number and for a given gamma ratio of specific heats. Doing the same exercise with static density ratio and temperature ratio, I can find out that change in density or fractional change in density or fractional change in temperature is also proportional to theta. Okay. Now an important conclusion from here we can see that if the same exercise is done with isentropic relationship which we have evolved with delta S upon R, I can write down this expression, because that is Cv or Cp ln T2 by T1 minus R ln P2 by P1. Inserting T2 by T1 and P2 by P1 expression here, I can obtain the expression something like this. Now again in the approximation, if I can use m1 sin square beta minus 1, then I can write down for all the cases, because sin beta is small, then I can write down m1 square minus 1, because if sin beta is beta is small, I can replace this thing with m1 square beta square, and that I am directly writing for m1 square minus 1. Now substitute this m1 square minus 1 as small m here, which I have done here. Now once you use for convenience to solve this entropy relationship such that m1 square minus 1 I am using as m and introducing this into this expression. By doing this exercise and solving, that is opening the series of this expression, that is the binomial expansion 1 upon gamma minus 1 as exponent of solving 1 plus x to the power n. And on solving in the approximate case, using the suitable approximation, I can reduce the relationship, retaining the first order term and ignoring the higher order term. I can write down directly as delta S upon R approximately equal to 2 gamma upon gamma plus 1 square m1 square minus 1 to the power cube upon 3. Now our objective is how this change in entropy is dependent upon the strength of the shock, and we have already deduced this relationship that the strength of the shock is nothing but gamma m1 square upon m1 square minus 1 into theta. Our objective in delta S by R for an important conclusion to bring down this term in terms of the strength of the shock. That is what exactly has been done here by algebraic manipulation. If you do this algebraic manipulation such as shown here, 2 gamma to the power cube upon gamma plus 1 to the power 3, m1 square minus 1 to the power 3 upon 3, which I have directly taken this term here, and then doing this and this term into this and this, I can see here that this term I can directly write as the strength of the shock, and hence in terms writing in the strength of the shock to the power cube, I can write down that delta S by R is approximately equal to gamma plus 1 12 gamma square in the bracket delta P upon P1 to the power 3. What we can see here, that for a first order change in theta, strength of the shock here, which shows me that the entropy change for a finite pressure change of first order is giving me a third order change in deflection angle. That is, the entropy is sensitive to the third order change in the deflection angle. What does it mean? It shows that for a small but finite change of pressure across a weak shock wave, for which a first order change of density and temperature gives essentially a third order change in entropy. That means if you are really interested to make the flow process to be isentropic, then a small change in theta will lead to a large change in the entropy. That is, if you are if rather than using the abrupt change in deflection angle, if you are changing the deflection, flow deflection slowly, it will benefit you a lot because it is proportional to third order of change in angle. So that is what essentially the idea to change that for a given theta, if you multifurcate into smaller pieces of theta in the successive geometry, that is, rather than having a sudden change in deflection angle to make the flow process, because in this process the oblique shock wave will make the flow field non-isentropic. However, you are interested in making this flow field into isentropic one. In that case, if you divide this deflection angle theta into a continuous variation of smaller theta here at various stages delta theta, then the amount of entropy change will be sensitive to delta theta to the power cube. That means how small delta theta, the entropy generation will be equally small, and hence we can generate or convert the non-isentropic flow field into an isentropic flow field. Note that in both the cases the shock waves are present. In the first case a stronger oblique shock, whereas in the second case a weak oblique shock, a collection of weak oblique shocks which are near to the wall, a weak oblique shock which are not orienting or intruding, imparting a small amount of disorder only, and hence near the wall the flow field will be is essentially isentropic in nature. That is what exactly used here, that is, rather than having a sharp change in the wedge angle theta, I am here showing that the linear variation, that is a small change in the deflection angle, such that the waves which are oblique shocks are created here near the wall will essentially will not change much entropy into the system, which is very essential, important from the propulsion point of view. Now going back to our discussion of the velocity component, velocity from upstream to downstream direction, I can further get some more useful information which has been done over here. Now V2 square upon V1 square I can write down from using the trigonometry, that is the normal component square plus tangential component. Since tangential component will remain same, I can write down Vx2 square plus Vy square upon Vx1 square plus Vy square, and this is giving me tan square beta minus theta plus 1 upon tan square beta plus 1, because I am replacing this fellow with Vx2 square and Vx1 square, and this can, using again the trigonometry, I can reduce this thing cos square beta upon cos square beta minus theta. Now moving further, to solve this, let us say if mu beta, if the shock angle can be written as a small Mach angle plus any small change in angle, which is I have termed here epsilon, where epsilon is much less than mu. Now taking sine both sides, I can write down sine beta is equal to sine mu plus epsilon, which I can open as sine A plus B, which is sine A cos B and cos A sine plus cos A sine B, and using that trigonometric relationship I can reduce this sine mu plus epsilon cos mu. And since sine mu, which is when the oblique shock is degenerated into the Mach wave as a limiting case, I can write down sine mu is equal to 1 by m1, and hence this expression can be converted into m1 sine beta is equal to 1 plus epsilon square root of m1 square minus 1. And now I can write down, if I write down squaring both side, I can again write down m1 square sine square beta 1 plus 2 epsilon m1 square minus 1. And also we know, we have already derived that m1 sine square beta minus 1 can be written as gamma plus 1 by 2 m1 square tan beta into theta. Now since the left hand side, by inserting this fellow here, replacing this flow on the left hand side, this left hand side will become equal. Therefore this term and this term I can equate, which will give me what actually I have assumed, the epsilon. I will get this term as epsilon is equal to gamma plus 1 upon 4 m1 square upon m1 square minus 1 into theta. Then hence what we have assumed, the small increment in the Mach angle which leads to me shock angle, I can get this angle from here. Now finally I can write down that cos square beta, again using the trigonometry, because cos square beta sin square beta plus cos square beta is always equal to 1, and we know this, that cos square beta can be written as 1 minus sin square beta here, and since sin square beta is obtained in the previous expression here, sin beta I can obtain from here in any of this relationship. By inserting this value here, I can get the expression of sin square beta. Once you substitute this expression in any of these two relationships, then I can directly write down m1 square minus 1 upon m1 square 1 minus 2 epsilon square root of m1 square minus 1. From these sin beta and cos beta, I can obtain the required tan beta, and hence the final expression of this velocity ratio v2 by v1, such that I can write down here that this v2 by v1 I can write down square root of cos square beta divided by cos of square beta minus theta, and replacing this cos beta and sin beta terms by opening cos beta minus theta, I can reduce finally the velocity expression from the downstream side to upstream side, such that v2 by v1 1 minus theta deflection angle divided by m1 square minus 1. This is an important relationship which we will be using subsequently. Now we can see here that what we converted essentially, that a continuous, a sharp change in the flow deflection which leads to non-isentropic flow field, I can change using noting that delta S is directly proportional to the theta to the power cube, as small as theta, as small as entropy change across the waves. Hence in this way, isentropic compression wave, by having this exercise which we have shown, that isentropic compression waves can be generated. Now what we find it here, that since the compression front has become isentropic in this case, but still note down the flow which is coming here is again turning into itself, which was the actual case, and hence the shock waves are present. Whereas if the flow, we have seen that the flow is turning away from itself, we have noted down that this kind of waves which we call expansion fans are present, which are the waves which relaxes essentially the flow. We said that these fans or expansion fans or waves, expansion fans or fans are isentropic in nature. But one more point we must remember here, that the flow consisting of expansion fans are not isotropic everywhere. For example, when there is a sudden change in the flow deflection angle, such as shown here, where the sudden change is there, at this point where this surface geometry is suddenly changing to cause the flow deflection, then at this particular point where all the expansion fans are meeting, we call, let us say, P, which is nothing but our vertex. So, at this vertex, when there all expansion fans are meeting, the waves gain sufficient strength, and hence whatever the flow passes over this vertex will no more be isentropic. That means in a case of centered expansion fans, the flow field is everywhere isentropic except at the vertex. Whereas to reduce this problem, I can again, likewise I did for a compression front case, if the variation in the surface is again continuous rather than sharp in this case, then the expansion fans which will be generated will be distributed something like this. And in this case, the flow field which is coming here upstream will be isentropic everywhere, including near the surface, because the waves are not meeting or coalescing into each other at one point, and since they are distributed over the surface, and hence the flow field away from the wall as well as near to the wall all are isentropic in nature. And these waves which we have just said it here, that these waves which are generated here as a distributed or a centered, these are commonly termed as Prandtl-Meyer expansion fans. Please note it down that these expansion fans are commonly termed as Prandtl-Meyer expansion fans. Now, likewise the shock waves which we have deduced, like oblique shock waves, relationship, static property ratios, density ratio, the density such as density ratio, pressure ratio, temperature ratio, stagnation pressure ratio. Likewise, these how to calculate the downstream properties when the upstream flow, supersonic flow, is meeting with these expansion fans or Prandtl-Meyer expansion fans. One such concept is to deduce the Prandtl-Meyer function, which is now our objective, to deduce how to calculate the Prandtl-Meyer function nu, through which we can calculate the static property ratio and stagnation properties ratio, that is eventually the flow properties. Note it again, recall that V2 by V1 we have deduced as 1 minus theta upon square root of m1 square minus 1. Now, if I take this fellow 1 and the left hand side, I can write down V2 minus V1 upon V1, which I have denoted here delta V upon V1 is equal to minus this term. Now, in differential form, for a limiting case when V change in the velocity is very small, dV by V is equal to minus d theta upon m1 square m square minus 1. I am dropping the subscript 1 here to reduce a general case. This differential form we can note that we are trying to reduce because, as I said, across the flow property changes across these expansion fans are finite but small. Hence, in the limiting case dV by V, I can write down again d theta by m square minus 1. Now, our objective is to integrate this. Therefore, if I integrate, I can write down minus theta is equal to square root of m square minus 1 dV by V, rewriting the original expression. If you integrate, this, then what I obtain here, minus theta plus an integration constant will come up, and then I can write down integral of square root of m square minus 1 dV by V, which I am writing here a function, Prandtl-Meyer function, denoted as mu, which is a function of Mach number, because Mach number is an important parameter here. We must remember this relationship, which we are going to use later. Now, we know that the velocity can be written as speed of sound, product of speed of sound into Mach number. Another form, from T naught by T is equal to 1 plus gamma minus 1 by 2 m square, I can again write down this expression as a square naught upon a square, that is in terms of the speed of sound. Now taking the first equation, consider the first equation, take log both sides and then differentiate. I can readily have dv by v is equal to dA by A plus dm by m. Now this dv by v and dA by A, this dA by A I am going to get from this expression, and using this expression into this, I can write down dv by v is equal to dm by m, and in the bracket 1 upon 1 plus gamma minus 1 by 2 m square. And hence please note it down that what essentially we have written, that nu m Prandtl-Meyer function, which is a function of Mach number, I can get if I multiply square root of m square minus 1 and taking the integration, exactly what I did it here. And hence the Prandtl-Meyer function can be written as integral of square root of m square minus 1 and this term on the denominator side and dm by m. If we solve this equation, then finally we will get the Prandtl-Meyer function as square root of gamma plus 1 upon gamma minus 1 tan inverse square root of gamma minus 1 upon gamma plus 1 m square minus 1 minus tan inverse square root of m square minus 1. The students must be encouraged to remember how to integrate these kind of indefinite integrals, and they must be aware of both normal as well as inverse trigonometric functions integral. And hence what we obtained here, that finally the nu m to obtain at any place which is minus theta plus constant, I can write down this using this expression. And hence what I can have deduce it here, for any subsequent downstream nu to calculate 2, I can write down upstream m and hence plus minus of theta, and this is the major or important relationship for calculating the downstream Prandtl-Meyer function, through which I can calculate the properties downstream side using the upstream properties that based on nu 1 Prandtl-Meyer function upstream and the flow deflection caused by these waves. Thank you very much.